Today, we're diving into the invisible forces that pretty much run our entire world. You know, everything from that little static shock you get from a doorknob to a massive lightning strike in a storm. It all boils down to electrostatics. That's the physics of electric charges when they're just sitting perfectly still.
I mean, think about it. That little zap isn't just some random quirk of nature. Nope. It's basically a tiny personal lightning bolt. And it's governed by a very precise, very fundamental set of cosmic rules. And today, by digging through a physicist's own notes, we're going to unpack those rules one by one.
So we're going right to the source. These are a physicist's actual handwritten notes, and it all begins with this idea of a time-independent distribution of charges. Now, that's just a really fancy way of saying we're hitting the pause button on the universe. We're looking at a world where all the electric charges are frozen in place. And in that frozen moment, there's one single, fundamental force that governs everything.
And that brings us to the very first tool in our toolkit, Coulomb's law. You got to understand, this is the absolute bedrock of electrostatics. Everything, and I mean everything, we're going to talk about starts right here.
Okay, I know. Looking at a page from a physicist's notebook can be a little intimidating. You've got all these vectors and Greek letters, but what's so incredible, what's so powerful, is that this one single line of math contains the entire story of the force between two charges. It is a complete narrative, all in one equation. So what is that formula actually doing? Well, think of it like a perfect recipe for force. It's amazing. You just give it two simple ingredients, how big are your charges, and how far apart are they? And boom, it spits out the exact force they're putting on each other, whether it's a push or a pull. There's no guesswork at all. So let's break down that recipe. Bigger charges mean a bigger force. Makes sense, right? And we all know the basics. Opposites attract, and like charges push each other away. But the real secret ingredient, the magic in the formula, is that inverse square part. If you double the distance between two charges, the force doesn't get cut in half. No, it drops by a factor of 4. It's a force that gets weak incredibly fast as you move away.
Now, Coulomb's law is fantastic for two charges, but what about a million of them, or a billion? Trying to calculate the force between every single pair would be an absolute nightmare. So physicists needed a smarter, more elegant way to think about the whole problem, and that's where the electric field comes in.
And that really is the key question, isn't it? Why invent a whole new concept? Well, it's because the old way was just too clunky. It was all about this action at a distance between two specific points in space. The idea of the field flips the script. It asks a much more powerful question. How does one single charge affect all of space around it?
And this visual just shows that leap in thinking perfectly. See, on the left, that's the old Coulomb's law mindset. It's just a straight line of force between Q1 and Q2. But on the right, that's the electric field. That one charge isn't just talking to another charge, it's creating this invisible field of influence everywhere, filling all of space.
The best way to think about it is like an influence map. The charge basically creates a set of invisible instructions, little arrows at every single point in space. Then, if you come along and drop another positive charge anywhere on that map, it just follows the instructions. The field tells it exactly where to go and how hard to push. It's brilliant. And the math behind this influence map is just beautiful in its simplicity. The electric field, which we call E, is just the force, F, that a test charge would feel, but then you divide out the size of that test charge, Q. And what that does is it gives you a pure measurement of the electrical environment itself, no matter what you happen to place inside of it.
Okay, so the electric field is a much smarter tool. But for some problems, especially those that have a lot of symmetry, there's an even cleverer shortcut. It's kind of like a physics life hack, and it's called Gauss's law.
And just by looking at the notes for Gauss's law, you can see that thinking has shifted again. We're not just looking at points in space anymore. Now we're drawing these imaginary bubbles, these surfaces, around the charges. The whole focus moves from individual forces to the total flow or flux of the electric field passing through that surface. And that really is the philosophy here. It's like, imagine you're trying to figure out how much water is spraying out of all the sprinklers on a big lawn. Instead of trying to measure every single little droplet from every sprinkler, you could just build a giant box around the whole system and measure how much water is flowing out through the walls of the box. It's a big picture approach.
So here it is. This is the absolutely astonishing insight of Gauss's law. The total electric flow coming out of any closed surface you can possibly imagine depends only on the total charge you've trapped inside it. So what about all those other charges floating around on the outside? Get this, they completely cancel each other out. They contribute nothing, zero.
It is a stunningly powerful way to just ignore all the extra complexity.
All right, let's move on to our final big concept, which really builds on everything we've talked about. This is maybe the most profound simplification of all. We're going to stop talking about forces and fields, which have direction, and start talking about energy, which is just a simple number. We're going to talk about electric potential.
You know, the absolute best analogy for this is a topographical map. The electric field is like standing somewhere on a mountain and knowing the exact steepness and the exact direction of the slope right under your feet. It's a vector. It has magnitude and direction. The potential, on the other hand, is like having the map itself, which just tells you the elevation, a single number, at every point. And from that much simpler map, you can figure out the slope anywhere you want.
And when we look back at the physicist's notes, yeah, the math looks pretty complicated. But the idea behind it is so simple. The whole goal is to trade that complicated map of force arrows for a much, much simpler map of elevation numbers. And that's what we call potential.
So here's the story of how you do it. First, you start with the electric field. Then you ask a simple question. How much work, how much energy does it take to push a little charge from one spot to another against the field's force? That work you do gets stored as potential energy. And potential is simply that potential energy, standardized by dividing by the charge. It's the energy landscape itself.
And this diagram from the notes just captures the payoff beautifully. The potential difference between point A and point B is literally just the amount of energy you need to spend to move a charge between them. It's the electrical version of asking how much energy it takes to hike from one elevation line on our map to another.
And there you have it. Our toolkit is complete. We've gone all the way from a simple force law between 2 points, to the powerful idea of a field that fills all of space, to a super clever shortcut with Gauss's law, and finally, to the beautiful simplicity of the energy landscape. These are the tools that let us understand a world where charges are holding still.
But that leaves us with one last, really fascinating question. All of these incredible rules we've talked about, they only work for a static world. What happens to physics when those charges finally start to move? Well, that's when a whole new force of nature enters the picture. And that is a story for another explainer.